Hello friends, welcome to the another session of Talent Tutorial classes. This is the continuation class for real number. In this session we are going to learn Euclid's division lemma theory and the exercises related to the Euclid's division lemma theory. So let's get started. So guys, let's try to understand this particular equation with the help of few examples. So if you see here are three examples: 17, 6. So basically 17 and 6 are two positive integers. So how we can write 17 in terms of 6? So let's go here. 17, we can write it like 6 into 2 plus 5. So if you try to correlate this particular line with this equation, you can say A equal to 17, B equal to 6, Q is 2 and remainder is 5. So how you can read it like 6 goes into 17 twice and leaves a remainder 5. So here A equal to B, Q plus R. Similarly, you can write the two equations as it is 5, 12. Here how you can write 5 and 12. 5 and 12 both are two positive integers. So if you want to write it like this in the form of the equations, then 5 equal to 12 into 0 plus 5. So here what you can see, this relation holds since 12 is larger than 5. So definitely 12 is larger than 5. So you need to make Q, which is 0 over here. Then only you can add the rest 5 remainder over here to make it as 5. Similarly, the third example, which is 20 and 4. So how you can write 20 in terms of 4? So 4 into 5 plus 0. So here in this case, remainder, there is no remainder, leaving no remainder. So basically 4 goes into 25 times over here and leaving no remainder. So it's quite easy to understand like how you can write two unique integers, or you can say positive integers, in the form of Euclid's division lemma. Yeah, so now we are on the next slide. So student, as I said in the start of the session, that this particular class is just about understanding Euclid's division lemma and few of the exercises related to it. So just now we have learned Euclid's division lemma, and in this slide you are going to learn Euclid's division algorithm. So these two topics alone, which are like theory over here, and then in rest of the session we are going to cover the examples. So I have just covered almost all the examples or the exercises related to this topic, and once you've done that, I think that's all. Your Euclid's division lemma topic is done for the session. Yeah, so basically what does the algorithm, Euclid's division algorithm, means? So basically this algorithm, it's a technique to compute the HCF of two given positive integers. So if we have two given positive integers, how to find out the highest common factor? That's it. The technique is called as Euclid's division algorithm. So basically we will try to correlate it with the Euclid's division lemma. So you would have learned already A equal to BQ plus R. So we will apply the same equation over here and try to find out how Euclid's division algorithm work. So basically C and D, in the previous slide we have taken it as A and B, but in this slide let's say C and D, and let's say that C is greater than D. Step 1, we will apply the Euclid's division lemma to C and D. So how we can write it down? Do you remember, student, last slide we have learned A equal to BQ plus R. Here nothing, it's just the same, just the C and D are now replaced with A and A and B are now replaced with C and D. So you can write in the same way, C equal to GQ plus R, where R is greater than equal to 0 and less than equal to D, less than D. Step 2. If R, which is remainder, if R is 0, then D division. D is the HCF of C and D. And in case R is not equal to 0, we have to apply the division lemma again to D and R. So don't worry, student, if you feel now it's little confusing. Going forward, I have given few of the examples by saying that it will be very clear to you how to understand Eclipse division algorithm. Okay, and to be noted it down, you need to follow this process until the remainder becomes 0. So you need to keep it doing. You need to keep on applying the Eclipse division lemma until your remainder becomes 0. So let's go to the next slide and see what's over there with the help of examples, how we will be understanding Eclipse division lemma with the help of examples. Okay, so rest two examples 19 and 81 are almost same. If you can see, it's exactly same represented in a way we have learned A. So I'm not going to spend much time over here. Let's quickly go to the next slide to understand the other examples. Question 2. Use Euclid's algorithm to find HCF of two positive numbers. So student, in this particular session, I'll be presenting you how to find out the HCF in two forms. One is exactly in the form of Eclipse division lemma, and the other one in the form of how we are doing our normal division. So by both way, you will able to understand how to find out the HCF of the two positive integers. So this particular slide is showing find out HCF based on Eclipse division lemma. So okay, solution. In solution, if you can see out of the two positive integer, this one is the greatest. So we will apply the lemma to 12576 and 4052. How you can write it? 12576, you can write it like this. So remainder became 420. So we are having some remainder with us. You remember, student, we have to keep on applying the lemma until the remainder becomes 0. So here this is not 0. So we will apply the division lemma again on D and R. So now if you try to recognize the initial examples that we were learning, A equal to B, Q plus R. We will keep on applying the division lemma on B and R until our remainder becomes 0. Next step, we have now applied 4052 and 420. Again, we got it in the form of this one. 272 still not 0. So we will apply again the division lemma on 420 and 272. So like that we are keep on doing until we got 0 in the remainder. So now the remainder has become 0. The divisor, the D part. Remember C equal to D Q plus R. The D part will become the HCF of the two positive. So now if the question is like what is the HCF of these two numbers? Definitely it's 4. Okay, so let's go to another slide and we will have a close look on the another example. Okay, so now question 4 is almost same as that of the question 3. It's just that here they have changed the question a little different than the previous one. So now let's read the question. So that any positive odd integer, that means any number which are 1, 3, 5, those are odd, right? So this is what they have given over here. Any positive odd integer in the form of 4q plus 1, 4q plus 3. So by looking at this itself, you can understand it's all odd integer, but you need to explain it. So how to explain it? Nothing. We just need to take the Euclid's division lemma and we will simply put it across and we will explain. So exactly again, so we will consider a positive integer and we will consider B over here is 4. So the moment A and B are available, how we can write R? R is greater than equal to 0 and less than B, which is 4 over here. So how many possible values of R? 0, 1, 2, 3. So now, very simple. Let's start applying the value of R and check how the equations is becoming now. A equal to BQ plus r. Here r equal to 0, so it will become a equal to 4q. Here r equal to 1, a equal to 4q plus 1, r equal to 2, r equal to 3. So we got 4 value of a, where q is quotient and r is remainder, for which we have already defined the value. However, since a is odd, a cannot be 4q plus 2. Okay, so in this question, basically we were supposed to prove that positive odd integer is 4q plus 3. But the moment plus 2 plus 0 is getting added into the numbers, they are not odd anymore, because you can start dividing this number and this number by 2. And the moment any number is divisible by 2, it's not odd anymore. Therefore, the remaining two numbers, which are 4q plus 1 and 4q plus 3, are odd. Okay, question 5 is a very interesting question. You will like doing it. So basically, a sweet seller has 450 Kaju Barfi and 153 Badam Barfi. So how they want to arrange their stack so that they can keep at least area of the tray. What is the number of that can be placed in each stack for this purpose? Okay, so you understand the requirement of the seller. Seller wants to stack them in a way that each stack has the same number. So stack is like stack 1, stack 2, stack 3, stack 4. So every stack should have same number of sweets. So how you're going to find it out? Very easy. It's just that you need to find the HCF between the two numbers A and B. So similarly, it's quite simple. You consider HCF of A and B, and here we have applied the Euclid's algorithm again. So 420 is the biggest number, so we will consider 420 as A equal to B Q plus R. So now R is not 0 over here, so we will again go back and do the Euclid's algorithm lemma on these two numbers, 130 and 30. 130 equal to 13 into 4 plus 10. Again not 0. We will go ahead and do again the division of 30 and 10. Here in this situation, R becomes 0. The moment R becomes 0, you just read this line, A equal to B Q plus 0. So B, or in some of the example it is called D, division. This becomes the highest common factor for the two numbers or the two type of sweets that seller wants to have. Okay, student. So this particular slide is basically trying to understand you how to find out the highest common factor. Let's quickly go to next slide, student. Okay, here are a few of these small examples. You remember in the previous slides I said you that there are two ways of representing the highest common factor. One you can show with the help of the Euclid's division lemma, and another you can represent it by the normal common way how we are doing the division. So here again we have to find out the HCF of 135 and 225. Here 225 is greater than 135, so we will apply division like that. 135 to 25, it will leave the remainder 90 and not 0. So what we'll do again? You try to recollect it or correlate it with the lemma theorem. Since the remainder is not 0, we will still do our division again. So now again we will divide 130 with 90. So here 45. Remainder is again not 0, so we will do one more time division, and in this case the remainder becomes 0. So the moment remainder becomes 0, at that point of time we can say the divisor, which is 45 over here, is the highest common factor of the two numbers. Next slide, again the same way of representation that we have seen in the previous example. 196, 38, 00, 220. So again here 3820 is bigger than 196. So we will divide it, and while dividing we noticed that remainder becomes 0. So the moment remainder becomes 0, do we need to do a division again? No, we need not to do the division again. We will stop here itself, and in one time itself we can find it out. The HCF of these two positive integers is 192. Going to next slide, student. Here is the third example, exactly the same approach as that of the. You want to pay attention over here, student. Look, 867 is greater than 255, so we will be dividing 867 by 255. It will leave the remainder 102, which is not 0. So we'll go back again and do division 51. This one is not 0, so we will do division one more time, and in this case remainder becomes 0. So we will understand that the division at this point of time is the HCF of two positive integer. Okay, now we are on question 7. In this question, we need to show that any positive odd integer is in a form of 6q plus 1, 6q plus 3, or 6q plus 5. We will again follow the same approach of the Euclid's algorithm, where a equal to 6q plus r. We have considered a as positive number, we have considered b as 6 over here, and we will go ahead with the values of r. So r, in this case, we got 6 values of r starting from 0 to 5. And how we can represent a then? A equal to 6q plus r. R is 0 over here, r is 1 over here, r is 2, 3, 4, and 5. So let's do one thing. In this below screenshot, you can see our value of 3 values of r being taken as per the queries. So r equal to 1, 2, and r equal to 1, 3, and 5. So the moment r becomes 1, the value of a will be 6q plus 1, 6q plus 3, and 6q plus 5. So what you will notice over here, none of the values of a are able to get divided by 2. So the moment you will not able to divide any number by 2, it's not an even integer. So the moment it's not an even integer, that means definitely there it's an odd integer. So that's the ask of this question, which we have proved over here in this example. Question 8 is again one of the interesting question, where the ask is like there is an army contingent of 616 members is to march behind an army band of 33 members in a parade. So basically there is a band of 32 members and total number of members are 62 members. So how they want the band, the 32 members should walk behind each other. So how they will be marching so that it is going to be a band of 32 members. So it's simple. I mean, we just need to find out the highest common factor and then the number which we will be finding it out. That way they need to plan their march of the band. So 616, 32, exactly the same way that how we have solved in the previous slides. So in this slide, you can see both the approaches. So whichever approach looks best to you, you can use the same in the examination. So first two line over here, it's using the Eclipse algorithm, which is written in the form of a equal to bq plus r. Here r is not 0, so we have again done the division one more time, equal to bq plus r. So r becomes 0 over here. So in this case, 8 becomes the HCF. And the another method over here, it's again very simple, which you can see here in the follow. Okay, so going to the next slide again, we are on the question 9. So this is again one of the important questions that is keep on coming in the exam. So you need to prove the theorem. It's nothing. I mean, in previous couple of examples, we have learned how to prove that any number, how can a number be a positive number or a negative number, positive number or odd, a positive even integer or positive odd integer. So in this example, basically what they are asking to show, the square of any positive integer is either in the form of 3m or 3m plus 1. For some of the integer m, where is m is like some integer. So how we are going to prove it? In this slide again, I have just given both the way how you can prove, either with the help of Euclid's algorithm, or you are going to follow the approach like that. So how we can write it down? So let's think that we have a number A over here and B is 3 over here, which is the ask 3m. So we will be representing it as A equal to 3m plus r, where the value of r becomes 0, 1, 2. So the moment we will able to find out the value of r, which are 0, 1, 2, we can represent A as 3q, 3q plus 1, 3q plus 2. These are the values of r, where q is the quotient. Now let's go here. Value of r equal to 0, r equal to 1, r equal to 2. Based on this value, how our equation become? 3q plus r, 3q plus 0, which will be equal to 3q. Similarly, 3q plus r, 3q plus 1, 3q plus r, 3q plus 2. So now we have three equations, a equal to 3q, a equal to 3q plus 1, a equal to 3q plus 2. So we will be squaring both the sides. Square, square and apply square. First case, it will become 9q square. Second case, it will become 9q square plus 6q plus 1. Third case, it will become 9q square plus 12q plus 4, because a plus b square equal to a square plus b square plus 2ab. Okay, so if you do look at the first case, you can write it down a square equal to 3m, where you consider that this is some integer n, 3q square. In the second case, a square equal to 3m plus 1, where how you can write m equal to 3q square plus 2q. In third case, you can write a square equal to 3m plus 1, where you can write m equal to 3q square plus 4q plus 1. So we are able to prove it. Wow, we are on the last question of this slide. So in previous slide, we have learned about the square of any number, but in this slide we'll be learning that how to show the cube of any positive integer is in the form of 9m, 9m plus 1, 9m plus 8. So again, same case over here, we will consider any number as a and we will consider b as 3. So then the Euclid's algorithm will become a equal to 3q plus r, and the value of r will be less than 3 but will start from 0. So 0, 1, 2. So we have three values of r, 0, 1 and 2. Similarly, as per the last slide, we can write it the equation as form of a equal to 3q plus r, where r equal to 0. So it will become a equal to 3q. Here a equal to 3q plus 1, and in the third case a equal to 3q plus 2. So now we have to apply cube. We will be cubing on both the side, right hand side and the left hand side of all the three values that we have. This will become 27q cube. This will become a cube equal to 27q plus 1 plus 9q into 3q plus 1. So how we can write it down? In all, 27q plus 1 plus 27q square plus 9q. So what we are going to do over here, we are going to take out the common out of these numbers. You can say 9 is common. So we will be taking out 9 common from here, and it will remain 3q cube plus 3q square plus 3q plus 1. And how we can write it down? 9m plus 1. We have taken this particular value or representing this particular value as m. In third case, where r equal to 2, we have done the cubing on both the side, and you can see the values over here equal to 27q cube, 54q square, 36q plus 8. So again, in the first three numbers, we will be able to take out 9 as common factor, and it will remain as these many numbers and plus 8. So we can write it out m because m is like any integer over here. That's why we will be able to take out m, whatever is left over here. So what you can see, aq equal to 9m, aq equal to 9f plus 1, aq equal to 9f plus 8, which is the ask over here to show that the cube of any positive integer, this a is positive integer we have taken, right? Cube of any positive integer is in a form of 9m, 9n plus 1, 9m plus 8, where m is any integer, which we have written it down over here. Okay friends, then we have covered the theorem and the most important examples related to this topic. Request you to go through and have a revision. Once you will do a complete revision of this particular session, I'm sure you will be able to handle any questions related to this topic. Request you to like, share and subscribe my channel if you are liking these sessions. I'll go ahead and bring a continuous session of the another topic for Unit 1 soon in my next classes. By the time, please take care. Have a good day. Bye.